Hello everyone, welcome back. So let's start on a new topic now. So we'll talk about energy management in various mechanisms, and this is a very important topic. So what we realize that there are many mechanisms we use in machines, and balancing is one of the key tasks. And if you are looking for precision or even for high speed motions, we want to balance them properly, and we might be looking at some mechanisms which are independent of their positions, and therefore we can categorize them into three parts. So one is like mechanisms with the constant potential energy. Next is the constant kinetic energy, and overall total energy constant. So these are the three main categories we can think of, and then we'll try to analyze one by one. So if you are looking at constant potential energy mechanisms, so if you look at this example, the mechanism here, what we see that a bar AB, if you see here, so any point on that bar, that link AB, if it moves and it slides on the vertical and the horizontal surface, so there are rollers, so it can move smoothly. So it generates a elliptical path, and that's why it's called a elliptical motion mechanism. And if it's the center, then we can get even the circle. So it's a very good mechanism. And so can we make it position independent or orientation independent? So let's consider springs, and two springs we choose, spring A and B, with the same stiffness, and when it's not attached to A and B, or suppose if A and B approach O, so that is the initial length, or or we can say that is a free of stress. So this is the initial length of this spring. So for A is this is the length we are talking about, and for length B, this is the length we are talking about. So these two lengths, initial length, but they are away from O, in a way is behind. So any extension, when we attach these springs to A and B, so the extension is X and Y. So the the measurement, the extension what we are taking is the total deflection. So later we'll be talking about ideal springs or zero length springs. So if this is the configuration, what we find that the potential energy, if we write so at any arbitrary position at an angle phi, what we see, this x is the displacement in spring A and y is the displacement in spring B. So it's already extended. So we can write the total potential energy half Cx square for spring A and half Cy square is the potential energy of spring B. We can write x square and y square because that is the total deflection in that spring. So here the spring A and B, the way it's configured, we can say is a zero length spring or ideal spring. So if that is the case, x and y we can write in terms of phi. So length is fixed, so x is L cos phi and y is L sin phi, And now if we write, put these values, what we find that is a half c in terms of L and phi. X is L cos phi, so it's a L square common. So we'll get ultimately inside cos square phi plus sin square phi, and we all know that this is equal to 1. So what we get is half CL square, and it's independent of phi. So no matter how it's oriented, how it's positioned, the potential energy is always constant, half CL square. So it means the potential energy, total energy, is not dependent on this phi. So it can stay anyway. What does it mean? So if we take the derivative of this, so with respect to phi, it gives us the force or moment. If it's with respect to displacement, then it will give the force. So first derivative, since it's u is constant, so this is 0. So ideally, no force required, no torque required to do that. And definitely the stiffness is also 0. The second derivative is also 0. So it's a 0 stiffness mechanism. So very nice, and I think good thing is we can place it anywhere. No, so of course in real mechanism there will be friction involved, and because of the friction it will hold. So maybe that is required, but good thing is it can be positioned anywhere at any position. And what we realize that because of this region, every position is an equilibrium position, so it will stay there. So that is the benefit. If we have the constant potential energy mechanisms, if we are able to achieve that, we can achieve 0 stiffness and it can stay anywhere. So what are the other configurations? What are other possibilities? So for instance, if we take these two blocks, 1 and 2, and suppose we preload them, attach them at M. So preloaded mechanism with the springs, two springs, CA, AB and CA, CD. These are the stiffnesses of those two springs, AB and CD. And suppose they are preloaded, and we want to achieve any position, or we can say without any preferred position. So whenever we attach many springs, generally it will have the lowest potential energy and it will always try to go back there. So if you want to eliminate that, if you want to have no preference with respect to the position, then we have to get a constant energy mechanism. So if this is the case, and these two links connected at M, and the wedge angle suppose alpha and beta, and the angles made is phi and psi, and this is the condition, then what will happen? So one of the assumption what we are making is AB and CD, they are ideal springs. It means if it's unloaded, the length is 0. It's a 0 length. So whatever is AB, that is the total deflection extension. So that we have to remember. So ideal spring, 0 length. So or many times in the literature we call it 0 length springs. So if that is the case, and suppose if you want to write uh, the total potential energy, so for spring AB, it's a half the stiffness of AB, CAB, and times AB. AB is the total deflection because of this condition, ideal spring, 0 length spring. Similarly for CD, it's a half CD times this length CD. So we talk about this length, AB and CD length square, because that is the deflection, total deflection. So your potential energy of any spring is given by half K delta square. But since it's a ideal spring, whatever is the length, that is the total deflection. So that's why we can simply put AB and CD there. So this is the potential energy. And if you look at the triangles and just look at try to rewrite these numbers in terms of link lengths and the deflections, what we find that if we write CAB times AB square, so AB square, CAB and AB square can be written as this triangle if we take. So it's A square plus B square minus 2A. A is the link at the length A and B into cos phi. So the angle there. Similarly, if we take the other triangle, here the CD square, this length can be written as C square plus D square minus 2C into D into cos psi. So remember that. So this is from the geometry. So we can refer to any book, geometry book, and we can find how it's related. So we can substitute that here. And once we have this, and what ultimately we want to have is this has to be constant. So if the total potential energy has to be constant, and if these are the things there, the variable what we find is it should be independent of this phi and psi. So how to get that? So if we just put half half and then try to add, if we add them, what we realize that these two parameters, they have to cancel. All others are constant. They are not a function of the angle. So, and it has to cancel. So it means both are negative. So one has to be positive and they should be equal. So in magnitude, they should be equal and opposite is sign. And if we do that, what do we find? CAB times AB. So what we have here, and CCD times 2CD, that's here, they should be equal. So that's the first condition. If we, so then the both parameters, these two numbers will be same. If we get this condition, CAB times A times B is equal to CCD times C times D. So very easy to remember, CAB times A times B, that has to be equal to CCD, the stiffness, and these lengths C and D. They have to be equal. Once they are equal, the numerators are same. Now cos phi and cos psi, now they have to be equal and opposite. So it means cos phi should be minus cos psi. And if that is the condition, what we know that 180 minus theta, so cos 180 minus theta is minus cos theta. So it means the phi is pi minus psi, and which gives us, if we do that, then we get phi plus psi is pi. This is the condition we get. So those two angles, the sum of those angles should be pi, or because the total angle is 2 pi, right? So alpha plus beta plus psi plus phi, and if phi plus psi is pi, then alpha plus beta should be also pi. So if these two conditions are met, what we realize that these two terms will cancel each other and we will left with only the constant parameters. So what will happen in that case, that again is written, okay, these are the assumptions. So these are the ideal springs and unloaded length is 0. In that condition, if we write the potential energy, total potential energy, and if we satisfy these two conditions, what we find that the total potential energy will be constant. It will be in terms of CAAB, A square plus B square, and similarly, so all constant terms only in the bracket. And once you have that, once it's a constant, what we realize that del u by del phi, that gives us the moment, that will be 0, and the second derivative which gives us the stiffness, that will be also 0. It means 0 stiffness, and it can be positioned anywhere. So it's independent of now phi and psi, and it can be anywhere. So if we ensure that this, so the two conditions C A and AB times ECD C into D, they are equal, and these angles of the wedges alpha and beta, the sum is pi, then the total potential energy will be constant no matter where we put it, how we orient it, the total energy will be always constant, potential energy, and therefore the every angular position is an equilibrium position. We can put it anywhere and it will stay. So very good mechanism, and this can be used for many applications for joints where we don't want to have any kind of preferences in position. So now the question is how to achieve the ideal springs, unloaded length equal to 0. So whenever we have this ideal spring or 0 length spring, what is the advantage is, whatever is the deformation, whatever is the length of the spring, that is the deflection, and we can straight away use and can get a very beautiful mechanism what we discussed just now. But in reality, getting 0 length spring is impossible. How to get something with 0 length? So yes, we have to find some tricks, some way, and one of the way was to put it back and then start from the 0, right? The other possibility could be like, if we see here, so here's the spring, and then it's a start like this, and this can be pressed, and then we can get it this one, and then can connect the parts like this and like this here. So this L is delta L all the time of the individual springs, and here F is the stiffness times L. So this is one of the way. Another way, what we did in the earlier cases also, like if we have this thing and this is the pivot, so this is the initial length L0 of the spring, and if we just pull it and hook it to B, this is the, we can use the same extension, and the force will be F times L, whatever is the position of B with respect to A. So in all these cases, what we realize that this spring is behind, and suppose if we put it over a pulley and then we just attach it, so whatever is delta L, I think that is the extension, and we can this L, so if you are measuring from A, whatever is the length, that is actually the deflection, and we can straight away use L for the deflection, and we can say that it's a zero length spring. So there are some examples, and we have covered, and talk about this coupling. So what we also realize that it has no preferred shaft angle, and why? So I think very easy to see here that what we know that this is, if you remember, these are equivalent to wire flexures. So 4 flexures here, and alternately connected like this, the two shafts. So what happen if it's connected like this, and suppose there is an eccentricity, and if we write in terms of y and z, so in the orthogonal direction, in the horizontal direction there is y displacement, in the vertical direction you have the y displacement. But we also know that this total eccentricity, mm, mm, Pythagoras theorem, if you apply, what we can write is E square is equal to y square plus z square. And if the stiffness of these individual wire flexures are same, dimension, the length and the area of cross section same, and same material, so it's made out of a single sheet material. So same, so C will be in both cases the same. So if we multiply and if we write half C y square plus half C z square, actually these are the potential energy stored on the individual sets, right, in y and z, and this is the total potential energy. And what we realize that once we write it, we can always write half C and y square plus z square, and we can replace this one with the E square. So this is what we get, equal to half C square, the eccentricity. And if this is the case, what we realize that there will be no additional torque because of this mechanism, because it has no preferred shaft angle. So no matter where the two shafts are there, whatever is the offset or misalignment there, it will be absorbed here, but at the same time it will not put any additional torque or moment on the setup. So because it has a constant energy, so it will be always same, and if you take the derivative, it will be 0, the first derivative and second derivative. So there is no preference for any orientation. So again, very good example illustrating the concept. So in reality, if you want to use this kind of concept, how it can be used. So suppose if you want to have this ball hinge for a satellite and antenna tripod, so you want to move around, and we don't want to have any preferred angle. So what to do? So of course, in that case, we can use this zero length springs, and it can take any position. There is no additional loading because of this. There is no preference, so it can move freely. Of course, the friction and those things are involved, and that can be also taken care by using some other means, by using proper flexure joints. Next is kinetic energy, and mm, how is observed, and how we can get it. So total kinetic energy is constant, and suppose this is a example, suppose mx, this is the mass mx suspended and moving in, can move in x direction, and we have my moving in y direction. But we also see that the x displacement, y displacement, and so if we write the total potential energy, so they are coupled, connected like this. So at any given time, what is the total kinetic energy? So it's a half mb square. So v is x dot square, so mx has only that motion, and similarly the block which is moving in y direction it will have only vertical motion, so y dot square. So if we write x and y in terms of r, so it's a couple, so therefore we can write x as r cos omega t and y as r sin omega t. And if you take the first derivative, so x dot, that is the velocity, is minus r omega cos sine, and omega will come out, so we have r omega sin omega t. And for y dot, for sine, the derivative omega will come out, and we have r omega and cos omega t. And if you take the square of it, and if we assume that mx and my is constant, they are equal, so same mass, then what will happen, we can take m out if we just plug it there. So half m omega square r square, we can take all these thing out. What will be left inside is sine square omega t plus cos square omega t, and sine square theta plus cos square theta equal to 1. So in many of the mechanism, if we are able to get this kind of a formulation, what we realize that in many cases we get the mechanism with the which is independent of theta, and then we can get constant energy mechanism. So in this case is the total kinetic energy, and what we find that it will be simply half m omega square r square, which is constant. There is no phi term coming here or omega t term coming here, so it's not dependent of that angular position or anywhere we are putting it here. So again it's a constant energy. In many of the mechanisms we talk about balancing of reciprocating mechanisms or four-bar mechanisms. So when we study about kinematics and dynamics of machines, we talk about that, the balancing. And in many of these engines, we have issues, and we try to minimize the any eccentricity, any mass offset if you can balance. And so for instance, if you take a V engine, and if you want to do the first order balancing, so of course there are first order, second order things are there, and we have to look at the literature and the textbook. So if you are really interested in balancing, so first looking at the first order balancing, but we realize that if this is the counterweight, the mass m we put, and if you want to write, what we realize that along x and y, is a minus m omega square r. So omega is the RPM. So m omega square r, that a centrifugal force, and it will be balanced, and then cos and sine x and y. So if we have that, and if you try to get f, what we find that inside again we have sine square and cos square, and then what we find that the total force is always constant, half m omega square r. So we should be able to balance it properly, since it's not dependent on theta, and therefore it's balanced all the time. So same force we are experiencing, and then it can be nullified. So suppose if we want to have a a mechanism with constant sum of kinetic and elastic energy, potential energy. We can couple them. So, like we can put these two in a similar way. So, we have the spring with the stiffness C, and then this is the mass is rotating, and because of that this is reciprocating with the speed Vx. So, if we write the total energy, so this is the kinetic energy half mx dot square, and this is the potential energy stored in the spring, which is half Cx square. So, whatever is the displacement, that is the energy stored there. And we can also write x, we can write in terms of omega t, so r cos omega t, and if we take the derivative of this, we can also get the velocity, which is minus omega r sin omega t. So, if we take the sum, want to find the total energy. So, half m omega square r for this, and x dot. So, we have sin square omega t here, and similarly for potential energy, if we take this, it's half c s r square and cos square omega t. So, what we find that again we have the sin square and cos square term coming, and if somehow if we can get the coefficients same, then we can take everything out and we are left with sin square omega t plus cos square omega t, which is equal to 1. So, the condition is the coefficient half m omega square c r square. So, we can write half m omega square r square is equal to half c r square, and if we just check, half will get cancelled, r square will also cancel. So, we are left with c equal to m omega square. So, if we get this, if we can make sure that the stiffness is parameter of m times omega, whatever is the rotational speed omega we are looking at. So, m omega square, or conversely what we can write, this omega has to be under root c by m. So, we can also relate with respect to the resonance frequency, the fundamental frequency under root c by m. So, if that condition is met, what we find that T plus U is also constant. So, total energy is always same. So, there are some more examples where we are talking about the energy, and as we started today, we are talking about different kind of energy in the system. So, energy management is mechanism. So, like gravity compensation is also a very important topic, and we use it many times. So, very straightforward gravity compensator, and we use it in many of the systems, in the lifts, in the any kind of elevators. So, this is the mass we have to move up and down. This is the servo motor we have. Just to nullify the effect, we have the counterweight here, same mass. So, what will happen if we just look at the quasi-static condition, we move it slowly, actually no effort required, right. So, more or less constant whatever is the friction force required. So, it can move very freely and can stay at one location at any point. So, and so it's a very good gravity compensation method, same weight. Only problem with this case is the inertia effects, the equivalent weight coming to this is again m, but we are carrying the two masses. So, whenever we accelerate, both has to move with the same velocity. So it means if we write the inertia and inertia value, so it's 2m, we are moving simultaneously with the same speed. So that is the downside. We have more weight to take care. But yeah, it's for slow moving things, it works. It's really nice. Now, very good example, and maybe not very intuitive, but what we see in this design is the effect of transmission. So, if you want to do gravity compensation by counterweight, there can be various methods. So, this is the first one. What we can say is the normal method, what we just discussed. So, on the opposite side, we put the same mass. So, whatever mass we have, the other side we also have the same mass, and it balances. So, quasi-static condition. So, it has constant energy. So, we can move it anywhere and place it. But effective mass on the servo, that is 2m, because the two masses you have to move. So, this is 2m. On the other hand, suppose we use some transmission and reroute it and then get cabling and the belt and pulley systems, cable and pulley system, and put it in a way that we use 2m. So, here the mass is now 2m, but it balances the same mass because of this thing, because of this cable and pulley arrangement. And if we do the force balancing, we can find it. What are the forces coming? So, what we realize that so effective for the quasi-static conditions, we get the same m here. So, it balances it, the mass at A, and although the total mass here is 2m, at B it's 2m, but on this side is only m. So, it balances. But what happens when it starts moving? The inertia effect. And there what we realize that although it's a 2m, but the transmission ratio is half, is b by 2. So, the equivalent, the effective mass working here on the servo is 1 by 2m, because what happens, you have 2m, but then there is 1 by 2 square. So, 2 get cancelled and ultimately we are left with m by 2. So, actually the inertial effect is a 3 by 2. So, if we compare here these two, what we realize that although we are using a bigger counterweight, but the inertia effect is reduced and we are handling only 1.5 m mass, but in the usual case, which is this, the effective mass is 2 times m. So, not very intuitive, but if we are aware of the mechanism, how it works, and what is the effect of the transmission on the effective mass or inertia, we realize that many times it can be smaller. So, in this case it get reduced to half compared to, although the real mass is 2 times 2m. Yes, downside will be the extra weight we have to handle. So, the load on bearings and those things. So, of course, we have to take care of that and we need to understand. So, there are other kind of gravity compensator also, and we can use the springs and what are the how it has to be done, how it depends on the various parameters. We can discuss on that. So, we'll stop here today. and we'll continue with these examples in the next lecture. Thank you.